we do the very fine tuning with that echelon.
Okay, well, thank you so much once again, Jennifer. I think we'll move on now to the next talk, but thank you again for a really interesting talk.
Yeah.
So our next speaker is going to be Xavier Porte, who is going to present the work on neural network computing with large area VCSELs. And it's a collaboration between the Institut Femto-ST and the Technical University of Berlin. Xavier, the floor is yours.
Thank you. Thank you for the presentation, and thanks the organizer for organizing the workshop. So I will talk about neural network computing with VCSELs, with large area VCSELs, in fact. So this is a work done in collaboration between our group at Femto-ST and the group of James Lott and Stefan Regenstein and the student Nazib Hagigi in Technical University Berlin, where they made the VCSELs we use. So I want to start with some motivation on why it's interesting to do hardware systems with physical systems to reproduce neural network computing. So neural network computing is extremely successful nowadays, and actually the growth of the, let's say, of the computational power needed to train machine learning or nowadays deep learning models has changed the scaling actually in the last 10 years. So it scales much faster than Moore's law is scaling for generating new hardware. And in fact, when you see a dependence in a plot like this, where you have the different hardware approaches still to train and to operate algorithmic neural networks, you see that most of them, when you plot it in power consumption versus their peak performance in number of operations per second, you see that they more or less fall in the same region. That means when you think like what is ideal in terms of efficiency and the speed, which is here on the upper left corner, most of the hardware systems actually do not go in that direction. So they have positive either in performance or in efficiency, but the ideal is still there. So that means there's a lot of room and there's a strong motivation for developing physical systems for neural network computing. Actually, I took this picture from this recent book on reservoir computing, theory, physical implementations and applications from Professors Nakajima and Fisher. And I use that for motivate this special type of neural network computing we do in physical systems. Actually, it's called reservoir computing. And interestingly, it mixes concepts of machine learning, nonlinear dynamics, and physical systems. In this case, optics falls here, and laser as we use them for our neural network or reservoir computing as in this area here. So it is a very rich approach that is around 20 years now. And I will briefly explain just to everybody be familiar how it operates. So original two seminal papers for current understanding of reservoir computing are these two. And actually the concept is similar to neural networks in many aspects. So you have some input layer where the information is injected into the system. Then you have your reservoir, which in our words will be a physical system. So all that is actually artificial neurons. So, and in the case of a reservoir, you understand it as a complex recurrent neural network. Actually, the computing with the system is done by training the system. And in reservoir computing, this training is restricted to disconnections here, so the output layer. So that makes it especially advantageous for hardware systems, as you can use a given complex system with many complexly connected elements as your reservoir, and then basically training the output allows you to go to the specific transformation you want. In this case, let's say you want to classify digits, for example, then whatever the digit you put, then you train that weights here so that your complex reservoir is correctly classifying the digits at the output. For us, the objective is to use photonic system because of its speed and the parallel operation intrinsic in optical elements. And also we want to go towards autonomous operation, as this meaning that you want to reproduce computer from all the steps in the computation. So the physical system is actually doing most of it. So why a large area VXL could be a reservoir? So if you have in mind this set of complex neurons, complexly connected, so what we want to use is actually the surface of our pixel. So that's why we're interested in rather large area devices, and particularly this would be a continuously distributed reservoir. So of course this is a continuous surface. So you have the complex mode pattern out of that surface, and that is what we want to use to compute. And we use these devices made at TU Berlin, which are follow this simplistic approach presented already some years ago of the group of James Lott, and actually they are very efficient devices and very fast. So they actually are typically on the high bandwidth for pixels, which are already fast type of lasers. So they are also efficient. So here we see comparison for different diameters, so 13, 23, 33 micrometers. So they are still efficient. So they have thresholds below 10 milliamps for such a big diameters and large output powers. And the 3dB bandwidth you see is still keeping beyond 10 gigahertz for example, in the case of beyond 30 micrometers diameter. How do we implement actually a reservoir computer with a large area VXL? So we have to keep in mind this architecture I showed before, and the fact that we want to use the spatial aperture of the VXL to do the computation. Okay, so we have to inject that information on that spatial aperture, and so what we do is to use an electro-optical component. So in this case, DMDs, so discrete micromirror devices. And we build these kind of patterns on the device, and then because of let's say the standard requirements for reservoir computing, we mix that certain pattern we have done here. Here you see like is a bit pattern, so you have a ring which we call TC lock, and of course that is injected by injection lasers. We forgot to mention that. So we have a certain DC log ring which always gives a certain level of injection on the pixel. Then we encode the bits here, and we will ask the system to do different tasks. For example, to recognize that certain bits, so 1001, for example, or to do other operations. I will explain later. And then we do this mixing of the input, this random mixing of the input with multimode fiber. We project that on our reservoir, which is the VXL, and then the readout weights are controlled by another discrete micromirror device. And finally, we put all together in a detector, and we basically train that part of the system. Okay, that's what we show later. So we have typically, depending on the diameter of the VXL we choose, several tens to up to 1,000 potentially of nodes. And we have, of course, different nonlinearities that is intrinsic for semiconductor lasers. From the lasing threshold, so the alpha factor, or so gain saturation, etc. And also, of course, we base the internal connections of our continuously distributed system on fixed carrier diffusion or the cavity diffraction that will build up this connection. So as I showed before, like in a more complex version of the step, so here's the VXL, we inject with the standard cavity laser with DMD, and we read out with another DMD. So these results have been published this year in Journal of Photonics. So how this information injection looks like. So if we only inject the ring here, we see that we perturb the original spectrum around 920 nanometers of the VXL by injecting a thicker and thicker ring, DC. We perturb more these modes, natural modes of emission of the VXL, and that basically goes from the original spectrum to towards a certain clearly deformed spectrum. And actually, then we complement that with a certain AC signal. So basically, the bits we want to inject. Here is an example of 2 bits of 00, 01, 1011. We encode that on the DMD, and we observe the readout patterns. So once we find the optimal conditions for modifying that original pattern of the VXL and have clearly different images, that means intuitively that we are on a good position to start training the system. The training algorithm, I will be a bit quick here, but basically we call it online training. So we don't do let's say we don't use we use minimally the computer for that. So we do a very simple algorithm that randomly chooses a mirror of the DMD, the output DMD, and then measure the error for the given task. So if the error decreases, we keep the change. If the error increases, we revert the change and choose randomly a different mirror. So by doing that, we train the system, for example, here for classifying 2 bits, as I showed before, like we show a sequence of several thousand bits, and then we basically repeat that sequence and keep training the system until it recognizes down to a certain error each sequence as we want. And the interesting thing is this kind of online training is minimally requires the computer supervision, and actually the whole process is around a minute. So the same process done with a spatial line modulator in the previous versions of the setup was taking days actually to implement. So the system is already much faster now because, of course, of the VCSEL, even though we don't use the full bandwidth of that VCSEL, so the gigahertz. So it's still a steady state situation. And so we did different tasks with a certain, we say like decent errors for the first trials with 2-bit header recognition, for example. Then we did 2-bit XOR, which is a classical task because it requires more complexity, and then digital to analog conversion also of 2 bits. So then we try to improve in 2 directions, so improving the learning rules, so to make the system faster. And for that, we inspired now on the gradient descent algorithm. So basically, we try to go from our error landscape. We try to go faster when the learning is steeper, and we try to go in slower steps when the learning is so the error is lower. Actually, by doing that, in the example of classification symbol 10 in this case, we change this rate at which the error changes, the number of mirror changes with respect to the error. So we change that. So we modulate the number of, so the largestness of the jumps. And actually we find this kind of dependence where there is a optimum value around 10. So flipping 10 mirrors at a time when the error was bigger. So we characterize that in a bit more detail. So we find this optimal condition. So definitively that improved the time for learning quite a lot. And so this learning improvement we keep, and we will also, and then we also investigate another more laser related aspects. In this case, we investigate the dependence of the power of injection and the wavelength detuning of the master laser. So for that, we did this spectrograph measurements, basically changing the wavelength of the injection laser and measuring the effect of on the modes of the large area VCSEL, and also on the performance of the task. So by the mean square error. And we basically find, so initially we centered here, so in the conditions where we maximally affect the large area VCSEL modes, and by changing the 2 parameters at the same time with this kind of dependence with a clear minimum for the error. So when we are at certain wavelength around 918.9, so we have this ideal scenario and in a power of 7 milliwatts for the injection. So that is what gives us best performance. So this is basically our state of the art. So now we are trying to find the best conditions for computation. And yeah, with that, I summarize my talk. So I hope I convince you that we have performed neural network computing based on reservoir computing for injection-locked large area VCSEL with around 100 neurons. And we have tried different diameters actually. So we are now on several hundred neurons. We obtained fully parallel and autonomous operation with minimal control from the PC at total consumptions around 1 watt, which is very low actually for computing neural network. We do multi-bit task for XOR, for example, or digital to analog conversion. And actually, we are now finishing the complete picture of the system dependencies. So as I say, like pump wavelength, power, and also we are improving significantly the learning. And our next steps definitively two most important steps are first, actually using the bandwidths of the lasers. So going not to steady state computation, let's say, but actually using the dynamics of the laser. And the second would be going deep architectures. So adding more layers of lasers, and well, we are actually working now on both of them. So yeah, so with that we can also address more realistic neural network tasks. Yeah, and that is all. Thank you for your attention.
Okay, well, thank you very much, Xavier, for the very interesting talk. So we have time for just one quick question, if there is a burning question from the audience. Yes, Stefan.
Hello. So thanks again for this great talk. It was very interesting. Can you say something about in what respect you can still improve the VCSEL itself in the system? So are there particular requirements of, for example, the size or the mode structure that would be advantages?
Yeah, thanks for the interesting question. So from device point of view, our first search, and because we knew the fantastic growing technology they were doing at TU Berlin, so we went simply for large devices. Of course, then when you start working with them, you realize that, for example, you need quite a lot of power to get the system out of this natural mode, for example, that is centered at the ring, you know. Sorry, not centered, actually going around the ring contact. So, of course, different. I've seen recently an Optica paper from also Ingo Fischer and Tomek Ciszynowski, where they do these deformed cavities, for example, and then the modes there are evenly distributed. I would like a lot to explore, for example, in this direction, you know, where your modes are more like, you know, surface even distributed. And in terms of we don't care, for example, here on polarization or other aspects. Actually, this is also a very interesting direction to go. So because all these complex modes will have many different, yeah. So for example, the polarization will be an interesting thing to check there. Yeah.
Thanks.
Yeah.
Great, thank you very much. Okay, so we'll move on now to the next talk, which is going to be presented by Juan Alanis.
Recording in progress.
And the talk is going to be about weight-adjustable photonic synapse by nonlinear gain in a vertical cavity semiconductor optical amplifier. It's going to be, so this is work that is from the Institute of Photonics at the University of Strathclyde. So Juan, do you want to share your screen? Yep, good.
Yes, I hope you can hear me fine. Thank you for the introduction, Mariana. And hello, everybody. I'm Juan Alanis, and I am currently working as a postdoctoral research associate at the University of Strathclyde Institute of Photonics. I'd like to talk about the work we have been doing in the lab using VCSELs for neuromorphic photonic applications. More specifically, the use of these devices as photonic synapses for neuromorphic applications. I will first start with some background. So over the past decades, an increase in computing power has led to important leaps in machine learning and also the development of artificial intelligence. This has led to the development of systems which are capable of powerful human-like tasks, such as the classification of large amounts of data for correlation and decision-making, as well as object detection and classification, etc. However, current state-of-the-art CMOS-based technologies for machine learning algorithms require considerable amount of energy, a lot of energy to operate, and moving forward, more powerful AI systems will come at the expense of larger footprint and energy consumption. In terms of frequency, microprocessors' clock speed has not seen a significant increase in recent years, having plateaued since 2004. Hence, new alternative computing architectures drawing inspiration from the powerful computational capabilities and low power operation of the human brain are starting to get considerable attention. These techniques offer promise for future energy efficient and reduced footprint for machine learning and AI systems. Neuromorphic computing draws inspiration from the human brain, as I just mentioned, and it utilizes networks of interconnected nodes acting as neurons for information processing. Neural networks come in many shapes and sizes, but essentially they are systems that can be trained to perform powerful human-like tasks, and they can outperform conventional numerical approaches. Great efforts have been developed in neuromorphic computing platforms based on electronic circuitry. However, these technologies might experience limitations in terms of achievable bandwidth and crosstalk, and therefore new hardware technologies for neuromorphic computing have started to be explored in recent years. One of such technologies for neuromorphic computing is photonics. These rely on optoelectronic elements that exhibit nonlinear responses, including spiking responses analogous to those observed in biological neurons. Recently, photonic spiking artificial neurons showing both high speeds and low energy operation have been demonstrated in multiple devices, such as resonant tunneling diodes, semiconductor lasers, amongst others. These particular examples are depicted in the slide, showing their ability to deliver neural-like spikes directly in the optical domain in response to incoming perturbations. Photonic technologies can also provide weighting elements to form larger neural networks capable of complex neuromorphic functionalities. In these examples, optical input signals are broadcasted to the network in a feed-forward fashion and weighted using photonic elements such as microring resonators, phase change materials, and Mach-Zehnder interferometers. The resulting weighted signals are collected at the output of the system, and through supervised learning, the weights are updated to perform neuromorphic tasks such as pattern and voice recognition. The advantages of using photonic systems for neuromorphic computing is the improvement in bandwidth, the ability to work at high speeds, low energy requirements, with reported energies of picojoules per spike, and the elimination of crosstalk, just to name a few. At Strathclyde, we have mostly focused on photonic artificial spiking neurons based upon pixels operating at high speeds and low input energy, and operating at key telecom wavelengths of 1300 and 1550 nanometers. In the recent past, we have shown that VCSEL-based spiking neurons are able to perform complex tasks, such as encoding of digital data to reconstruct RGB images, matrix convolution to determine image gradient magnitude, as well as pattern classification. In addition, we have shown single VCSELs can be used to build recurrent networks for reservoir computing. In this setup, the VCSEL output is fed back onto itself, creating a delayed feedback loop, and it's able to perform successful complex tasks with good performance, low error, and for very low optical input powers below 100 microwatts, and benefiting from low threshold currents of just 1 milliamp. Now, we show that VCSELs can also be operated as photonic synapses. So basically, in biology, the job of a synapse is to strengthen or weaken the connection between neurons, essentially applying weights to incoming pulses before passing it on to the next neighboring neuron. Similarly, we're able to emulate this functionality with a VCSEL. When operated below threshold, vertical cavity lasers can operate as amplifiers, or VCSELs for short. The way this works is by injecting an optical signal from the tunable laser, which is frequency matched to the VCSEL's dominant resonance frequency. Then the tunable laser is modulated with a Mach-Zehnder modulator using signals from an arbitrary waveform generator. The AWG modulates the tunable laser to generate 150 picosecond pulses and directed towards the VCSEL using a fiber coupled system. The input pulse is received by the VCSEL, which applies a weight to the incoming optical signal. The weight control is adjusted simply by controlling the device's driving current below threshold. In this case, at values less than 95% of the device lacing threshold. This mechanism allows to modify the frequency detuning between the external injection and the VCSEL's resonance, yielding potentiation or inhibition of optical pulses at the output of the device. The resulting weighted pulse is collected at the output of the setup using a photodetector and an oscilloscope. As shown by the PL spectra, when applying a current value to the VCSEL of 2.245 milliamps, the frequency detuning between a tunable laser and VCSEL is small. Thus, the amplitude of 150 picosecond pulse is weighted by a factor of 100 1.79, hence producing gain. As the current of the VXOA is decreased to 2.210 milliamps, the VXOA PL spectra shifts to lower wavelength, resulting in an increased frequency detuning of around 5 gigahertz. And as a result, the input pulse is weighted down by a factor of 0.77. As the VXOA current is further decreased, then the output pulse amplitude is reduced further. With this, we show a VXOA can be used as photonic synaptic element to adjust the strength of incoming optical short pulses by simply tuning the device's bias current. Moreover, the system is able to amplify incoming signals. We surveyed the average output pulse amplitude for the full range of current values and found that the pulse intensity as a function of the driving current follows a nonlinear trajectory as shown by the Gaussian fit. In addition, we show that the system can achieve large tuning values for small changes in current, here shown by the red dotted lines, which correspond to the 3 cases I have shown previously and separated by a few tenths of microwatts. In the next stage of the experiment, we focused on demonstrating dynamical weight tuning capability with a VXOA-based photonic synapse. To do so, we used the AWGs to also modulate the VXOA's current between different weight levels. In this case, the device is modulated such that the current changes every 100 nanoseconds between our predetermined low and high levels. The low level is kept fixed, while the top level is increased by a certain amount, I mod in this case. Simultaneously, the tunable laser is modulated to introduce 150 picosecond pulses at a repetition rate of 200 megahertz, or every 5 nanoseconds in this case. Here I show time traces associated to the output of the VXOA, where the pulse amplitude is influenced by the VXOA current modulation, I mod, which goes from 3 to 27 microamps. And here I plot the median peak power for low and high regimes, and thus showing that these results does show that the photonic synapse is able to dynamically tune the strength of incoming optical pulses with user-defined signals. To show the system capability for fast weight dynamical tuning, we introduce a signal formed by 150 picosecond pulses and separated by 2 nanoseconds, and once again introduced a square wave modulation signal into the VXOA bias current, switching between a high and low value at 0.5 gigahertz. I have to point out that this limit is imposed by the electronic components of the setup and not by the VXOA itself. Then the output time trace shows that the optical pulses amplitude follow the VXOA current modulation quite accurately, which shows the potential VXOAs have to apply weight to incoming short optical pulses at high speed. Moreover, we are also able to apply multi-level current modulation, where we can selectively apply multiple selected weights to both single pulses as well as bursts of input pulses with different amplitude. In conclusion, we have shown an experimental demonstration of a photonic VXOA-based synapse using inexpensive off-the-shelf components operating at Télécom wavelength, and when operated as an optical amplifier, the VXOA is able to adjust the strength of incoming optical pulses or spikes by simply tuning the device's bias current, as well as providing signal amplification. We also demonstrate the system's ability for high-speed weight tunability, introducing user-defined signals. Therefore, we show that VXOAs have a great potential as synaptic elements for future neuromorphic photonic systems. Thank you everybody for your attention and to our sponsors.
Well, thank you very much, Juan, for your talk. So I would like to ask the audience if there are any questions. We have time perhaps for one quick question. Yes, Xavier.
So thanks, Juan, for the nice talk. And I'm wondering, so how consistent is this reproduction of the pulse? And if 100% of input, you get 100% of output, you know, like one pulse, or that depends on the bias, or?
I'm very sorry, I was in the middle of a cough attack. Can you please repeat the question?
Yeah, sure. So I was wondering how consistent is the response of the VXOA. So how that depends on the bias also. So for example, you get 100% reproducibility of pulse repetition.
Yeah, it's quite consistent as long as you position yourself at the same point. Say, for example, in this case, we're biasing at values below 95% or less than 95% of the threshold. So every time you kind of position yourself in the same spot, you can reproduce these spikes quite consistently. So yeah, I can say this is very consistent, yeah.
You don't have a quantification though? Yeah.
No, we haven't really quantified the consistency, to be honest. But we have done this with different devices, and depending on the device you're using, this can also change. Although you can still observe amplification and weight control, but depending on the device, this could also vary. So it's very hard to give a metric at this stage. Yeah.
Okay. Thank you very much.
No worries.
Okay, well, thank you very much again for the talk.
Thank you.
So I would like to now invite the next speaker, who will be discussing oxide confined versus barrier tunnel junction aluminium gallium arsenide VCSELs. And this is the result of a collaboration between the Polytechnique di Torino and the CNR IIT in Italy.
Yes, thank you for your introduction. I'm Alberto Gullino from Electronics and Telecommunication Department of Polytechnique di Torino. And this is our presentation dealing with oxide confined versus barrier tunnel junction aluminium gallium arsenide VCSELs, carried on in collaboration with National Research Council of Italy. So first of all, I want to provide a little bit of context. In fact, the staggering growth of the global internet infrastructure has made the short-haul communication dominant over the long-haul counterparts. Therefore, there is a continuous drive for high-velocity, efficient, and temperature-stable devices working in the data center. In this context, the state-of-the-art is represented by aluminium gallium arsenide oxide-confined VCSELs emitting in the 850 and 980 nanometers window, which are ideal for optical fiber coupling and also show low production, testing, and packaging costs. Furthermore, they are characterized by excellent dynamic properties. Oxide-confined VCSELs operate as spin diodes because electrons and holes reach the intrinsic active region moving across oppositely doped DBR. The optical and the electrical confinement are provided by the presence of an oxide aperture. However, these devices are characterized by two main issues. The first is related to the presence of lossy p-dop DBR, which is characterized by high resistive losses due to reduced mobility, which increases the Joule heating. And also in the PDBR, there is a larger free carrier absorption loss with respect to the end-doped one. The other issue of this device is related to the technology process needed to define the oxide aperture size, which relies on a wet oxidation process of the aluminum-rich layers placed in the device. And therefore, there is a not very reliable precision when scaling into small apertures. In this work, we explore the possibility of realizing oil injection by means of a barrier tunnel junction, which would replace the top p-doped DBR with an n-doped one. Furthermore, BTJ would provide the optical and electrical confinement thanks to the lateral refractive index step and also to a tunneling path, which is now photolithographically defined. But what is a tunnel junction? This is simply a heavily doped PN junction which works in reverse bias. In this condition, the main transport mechanism across the junction is represented by band-to-band tunneling, and this makes them essential components for multi-junction solar cells, for high-performance field effect transistors, and also for light-emitting diodes. However, they have already been proposed also for VCSELs. in particular for long wavelength VCSELs, where they were first proposed in 1.55 microns indium gallium arsenide phosphide devices, and also more recently in gallium antimonide devices. Even more recently, they have been included in 3-nitride VCSELs, where an effective p-doping is hardly achievable due to the large activation energy related to acceptor doping. And therefore, we want to investigate here the possibility of including a BTJ also in aluminum gallium arsenide VCSELs. This is done by taking into account that a solver for a VCSEL requires a multi-physics solver able to take into account the electrical, the thermal, and the optical problems that all play a significant role in a VCSEL operation. Therefore, we have decided to extend our one-dimensional drift diffusion solver called Diana, which is able to solve self-consistently the Poisson and the continuity equations in a steady state condition by means of a finite box method, which is stabilized by means of a Scherfetter and Gammel scheme, and solved by using the Newton's algorithm. This diffusion system has been extended with quantum correction to deal with the quantum wedge populations, which are coupled to the bulk ones by means of capture rates that are included in the generation recombination rates in the continuity equations. The information related to the quantum well population is needed to extract the active region gain from a lookup table, which is generated by means of the Fermi golden rule applied on electronic band structure computed by means of a K.P method. The active region gain, together with the parameters extracted from our VCSEL electromagnetic solver VELM, which provides the modal losses and the modal wavelength and the photon confinement factor, we are able to couple carriers and photons together and solve the photon rate equation. The results from this electrical and optical solver are used to compute the thermal sources which are needed to extract to solve the one-dimensional heat equation, which is here solved by means of a one-dimensional finite element method scheme. However, the modeling of a BTJ VCSEL requires a further step because the BTJ relies on the tunneling, which is a fully quantum mechanical problem and therefore needs a rigorous model. In this work, we have used the non-equilibrium Green's function formalism, with which we can extract a spectral density current across the junction, and then we can take this spectral density current, integrate it in a single band energy range, and extract a density current. This can be then differentiated across the tunneling direction, and when it is divided by the elementary charge, returns a generation recombination, a tunneling generation rate that can be plugged alongside the other generation recombination mechanism already included in the diffusion solver. The typical shape of a generation rate from tunneling is depicted here in the figure, showing how it is picked where the tunneling path is the shortest. So now I'm ready to discuss briefly about the two structures in which I reported the fact that the reference device, the oxide confined VCSEL, has been converted into a BTJ VCSEL only after the cavity, where the oxide layer here in the dashed lines has been replaced by a BTJ. Notice that there is also a 5 nanometer shift introduced to correctly place the node of the standing wave, computed again from VELM, in the BTJ position. This is done to effectively reduce the impact of the free carrier absorption losses that will be enormous due to the very large doping levels introduced in the BTJ. From this figure, it is not reported the fact that the presence of an end-opt DBR instead of PDOPT1 has made the overall structure shorter in order to match the gain at threshold and provide a more fair comparison between the two devices. However, the emission wavelength remains almost identical. Starting talking about the results, it is interesting to take a look at the energy band diagrams, which are here reported at the bias of 3 volts at 20 degrees Celsius, and here reported in the proximity of the active region, which is the most interesting part of the devices. Starting from the offset confined VCSEL, we can see again how electrons and holes reach the active region, moving across the opposite of DBR. Their transport can be effectively modeled by means of other diffusion model. Similarly, in the BTJ VCSEL, the electrons reach the active region again from the bottom end of the DBR, while Hole injection is now enabled by band-to-band tunneling across the tunnel junction, in which in the inset we have reported a band diagram of the BTJ, which is also the region which has been investigated in NEGF to extract the previously mentioned generation rate. So eventually I can move to the discussion of the optical and electrical characteristics. And first I want to focus on the IV curves, showing how the offset confined VCSEL actually works as an aluminum gallium arsenide PIN diode, as it starts conducting from 1.4 volts. Moreover, notice how the simulated one-dimensional result is very similar to experimental results, and we use exactly same parameters to simulate also the BTJ VCSEL. This it is clear that shows smaller values of current at equal applied bias due to the presence of 2 anti-series junctions, which makes the device conducting only when a sufficient bias drops across the tunnel junction. From the LI curve, however, we can see how the small electrical penalty previously described is largely compensated by a steeper LI slope, which is allowed by the reduction of the outcoupling losses in the top end of the DBR. And this allows to increase the maximum optical power from 3.3 milliwatts to 5.5. Yet keeping at the same value the threshold current due to the fact that we have matched the gain at threshold. At 80 degrees Celsius, we can see very similar results. Again, a good accordance between the one-dimensional simulation and the experiment. And again, the BTJ VCSEL shows smaller values of current when the same bias is applied to the structure. However, again, the BTJ VCSEL provides higher optical powers, and the maximum power moves from 1.5 to 2.2 milliwatts, even though it shows a slightly higher threshold current due to the fact that the gain at threshold were matched only at 20 degrees Celsius and were not matched again at 80 degrees to keep the device identical at the 2 temperatures. Eventually, it is interesting to take a look to the wall plug efficiencies of the 2 devices, in which are reported in this figure, showing how at both temperatures the BTJ VCSEL improve the efficiency. In fact, it moves from 23% of oxide confined VCSEL at 20 degrees Celsius to 31%, and from 15% to 19%. So there is a significant improvement in the performance. So the conclusion is from this one-dimensional simulation, the BTJ VCSEL looks very promising when compared to an equivalent oxide confined devices. device, showing same threshold current due to the matching of the threshold gain, and to higher Li slopes due to the reduced outcoupling losses. Also, the thermal rollover occurs at much higher optical powers. All these avoiding the oxide confinement technology, which, as we discussed, can pose some issues. The next step of our work will be directed through the optimization of the BTJ VCSEL by means of the presented one-dimensional drift diffusion solver. And then once the unoptimized version of this device is reached, we want to extend this diffusion coupling also to Venus, which is our three-dimensional, fully comprehensive VCSEL solver, in order to investigate the lateral features of this device. So thank you for your attention.
Well, thank you very much for your talk. I see that there is already a question from Joachim.
Yep.
Yep.
Do you hear me? Can you hear me?
Yes.
Okay. So yeah, thanks very much for your talk. It reflects some of the issues we struggled with at UCSB when we developed such tunnel junction VCSELs some years ago. And I'm especially impressed by your green function implementation into drift diffusion, because in general, it's very difficult to predict the tunnel junction resistance correctly. And the simple reason is because you don't know what the actual doping profile is. In the simulation, that is my question, did you assume ideal rectangular doping profile or more a realistic doping profile? Because the shape of the doping profile very much determines the resistance of the tunnel junction. Either way, whether you use green function or any other model. So what is your doping profile?
No, actually, it's a rectangular profile with incomplete ionization model, of course, and we have also taken into account the band gap narrowing induced by the strong doping, but of course we have not taken into account more realistic doping profile. So this would be interesting to do in future work, of course.
I think that is why your IV curve, your bias is always lower than people will measure it, because as a real doping profile is not as good as your rectangular doping profile. So this is the fundamental problem with all tunnel junction simulations. And I have another simple question. Your simulation doesn't really agree with your initial slide 3, where the tunnel junction is located above the active region. In your simulation, the tunnel junction is included in the DBR, which is not what is typically done. Yeah, but on your slide number 3, you show a tunnel junction inside the P spacer layer, and that is what typically is done. But your tunnel junction looks like a ring junction, a ring. There is a hole in the center. Why do you have that hole in the center? That's my last question.
Yes, this is actually only a representation, an image to explain the concept. This is not actually the device that we have investigated in our simulation. This is represented by the figure that represented the refractive index profile. This is actually the real profile the real devices we have investigated.
Yeah. But my point is, in reality, tunnel junction is not located into the DBR. It is because the DBR is undoped, is not used. You use a ring contact and put the tunnel junction above the active region, very close. But my question now is, why is there a hole in the middle of your tunnel junction on slide 3?
Okay.
Or is that just...
this is only, this figure here is not the actual device.
So there is no hole.
The top end contact is actually on the device we have investigated assumes the end contacts at the top of the DBR and the other end contacts at the bottom of the DBR. Okay, so
I know.
Okay.
Okay, but in the UC2 tunnel junction, why is there a gap in between?
Here?
Yes.
This is like two VCSELs in.
Oh, these are two different VCSELs in an array.
Yes, exactly.
Oh, I get it. Okay, thank you very much.
Okay. Thank you.
Okay, well, thank you very much. We'll move on now to the next talk. which is going to cover 1.5 gigahertz VCSEL-based laser system for ultra-fast multi-contrast nonlinear imaging, and is the result of a collaboration between the University of Arizona and University College Cork. So the speaker can now start sharing this.
Hi. Yeah,
hi, Thibault. Hi.
Hi. Am I sharing my screen? Is it working?
Yes. Yes.
Okay.
So there's a paper showing up.
Okay. Very good. So yeah, my name is Thibault Bondaz, and I will be presenting to you a 1.5 gigahertz VCSEL-based laser system for ultra-fast multi-contrast nonlinear imaging. My advisors are Jason Jones, Jerome Maloney, and John McKinney from University of Arizona and the University College Cork. Firstly, why should we use a high precision wave rate for nonlinear imaging?
Thibault, sorry to interrupt you.
Yeah.
Do you want to share a presentation, or is this what you want to show? Is this the?
I thought I was showing the presentation. That must be a mistake.
Okay.
Let me share again. Can you see something?
Yeah, now it's good. Yeah.
Okay, very good.
Yeah. Okay.
So, why should we use a higher precision wave rate for nonlinear imaging when typically the kind of laser system used for those kind of microscopy application have a repetition rate in the order of 100 megahertz or so? Well, that's what I'm going to try to convince towards the benefits of our laser in this slide. So the first obvious benefits is that a high repetition rate allows for high-speed imaging. If you can deliver your pulses faster to your sample, you can move on to the next sampling point faster. And since this exposure time is reduced, you also can reduce the amount of integrated noise in your imaging. So that allows for faster imaging and higher signal-to-noise ratio. A less obvious advantage is the reduced risk of photo bleaching and photo damage. Photo damage tends to scale faster with intensity than it does with exposure time. So a longer exposure time with lower peak power should reduce the risk of damage. Of course, provided that the peak power that you're using is still enough to drive the non-linearity in the sample that you're interested in. Low intrinsic intensity noise is more a property of the VCSEL than it is than a high repetition laser. But the VCSEL tends to exhibit low noise, intrinsic low noise properties that are very desirable for those kind of application. Another thing that might be interesting is that matching the wave rate for a typical fluorescent lifetime in biological sample that tends to be around 1 nanosecond or so could drastically improve the 2 and 3 photon excited autofluorescence, and that might provide some insight on tissue dynamics. Of course, there's some cons. The main one and the obvious one is that a faster repetition rate usually means a lower peak power. However, this cons can be mitigated if you can make sure that the pulse you're using are transform limited, meaning that the spectral phase is flat, and that means a higher peak power. So this is what the full setup looks like. So as I said, the main oscillator is a VCSEL. So V cavity mode locked passively with a saturable absorber. The pulse duration out of the VCSEL is 750 femtosecond, and the average output power is 90 milliwatts. The wavelength centers at 1035, and as I said, a 1.5 gigahertz wave rate. This output is coupled into a two-stage ytterbium amplifier, and we're using 2 pairs of compression gratings for compression. This allows for an output of up to 15 watts of average power and pulse duration down to 85 femtosecond. However, I tend not to use that much power. This is probably overkill for what we're doing. Nominally, the output power of our power amplifier tends to be around 55 watts, and I get a pulse duration of 100 and 110 femtosecond, which is enough for what we're doing without the risk of thermal drifting and all kind of high power possible damage that could happen to a facet of the fibers and so on. So this output is then coupled into a photonic crystal fiber for supercontinuum generation. We coupled 2 watts into the supercontinuum into the photonic crystal fiber and gets a bandwidth of 350 nanometers out of the photonic crystal fiber. This output is then coupled into the MIPS. So I'll talk about it in more detail later on, but basically this is what allows us to control spectral phase and amplitude of our pulse. So as I said, this is how we get our transform limit of pulse duration. We are retrieving and compressing the spectral phase of our pulse, and this output is then coupled into a 2-photon microscope for nonlinear imaging application. And I'll show some very early preliminary results that we got from the 2-photon microscope. So a few words on the oscillator, VEXL. So VEXL, in one sentence, if people are not familiar with it, it's a weak cell without the surface mirror. So a region of the cavity is in free space, and usually the dielectric mirror would provide the other side of the cavity. In our case, we're using a high gain distribution of quantum wavelength range in a resonant configuration for high gain to the design wavelength at 1035. Yeah, the stack of quantum well is stacked on DBR, and the whole setup is indium bounded to a CVD diamond. The mode locking status is achieved with a satchable absorber for Q switching the cavity. So for it would be nice to have very short pulse out of the VEXL, and so the cavity is dispersion optimized, and by that I mean that the angle of incidence on the VEXL gain chip is optimized so that the dispersion round trip is as flat as we can get it. There's also anti-reflection coating on both the VEXL gain chip and the satchable absorber. It's a bilayer coating of tantalum pentoxide and silicon dioxide. They are ion beam deposited, and yeah, they're designed to get shorter pulses out of the VEXL. The dimension of the cavity is designed to produce stable mode locking and single pulse transverse profile. And by that, I mean that the waist of the beam on the satchable absorber is so that we can saturate it, but not, the power density is not too high as to create excess gain where we could have multi-pulsing into our cavity, and that would be unstable and not desirable. Yeah. So moving on to the supercontinuum. So I'm not talking the amplifier, EWM amplifier is not very interesting. It's very standard. So supercontinuum generation is, as I said, generated with a photonic crystal fiber. Its length is optimized, length of about 45 centimeters or so, is optimized for maximum broadening and minimum phase distortion. This is done with numerical simulation. Yeah, we want minimal distortion because although we can make up for change in distortion in the spectral phase with our MIPS scheme, it still has a limit. And so if we can manage the distortion before getting to that point, it would be nice. Yeah. So moving on to the. I'm sorry. I thought someone said something. So moving on to the MIPS. So what does that stand for? It stands for multi-photon intrapulse interface space scan. So I'm not going into how the algorithm works precisely because I won't have time. But in one sentence, it's an iterative method to retrieve the spectral phase of an incident beam by applying a series of known spectral phase offsets to a spectrum and observing the resulting changes in its second harmonic generation. So in practice, how does it work? There's a beam coming to a grating. And the frequency is spread by that grating are focused on a spatial light modulator. So it's a dual screen liquid crystal based spatial light modulator. And by changing the voltage applied to each pixel of that screen, we can control spectral phase and amplitude independently from each other. And so with that control plus the ability to retrieve the spectral phase with an iterative method like the MIPS, we can compress pulses, we can splice the spectrum, and we can just apply any kind of arbitrary spectral phase to our incident pulse that might be desirable for a specific application. This is, for example, how successful compression will look with the MIPS. So in red here we see how the spectral amplitude, so of an incident beam. In green, the spectral phase before compression, and in blue after compression. We see that the spectral phase flattens, and that results in a shorter pulse duration that is close to transform limited. In a time domain, this is what it would look like. So in blue, the retrieved pulse based on retrieved spectral data with the MIPS algorithm, and in green, the autocorrelation. This is a 30 femtosecond or so, which tends to be typically what we get for in our setup. But so, as I said, this is an example for a bandwidth that looks like this, but we generating a supercontinuum. So this is how we can splice and compress that whole supercontinuum. So this is done by changing the voltage applied to the spatial light modulator. We see this is all the wavelength accessible, and there's a lot of desirable wavelength for biomedical application here. 900 nanometers. I think some interest for like exciting calcium in brain samples, and the longer wavelength 1200 and above. 1200 or so is used to excite the nonlinearity in deep tissues, muscles, and stuff like that in biomedical. Yeah, we tend to get a 30 femtosecond pulse duration across the board, near transfer limited. I should have precise. So the full line here is the spectral amplitude, and the dotted line are the measured spectral phase after compression. And all the pulse duration have been confirmed to be the duration that are retrieved with the MIPS with an autocorrelator. So as I said, I would present some very early 2D imaging, some very nonlinear imaging possible capability of our setup. So this is very early. The point of this presentation is not so much to do a presentation about nonlinear microscopy, but also to demonstrate the laser source. But we have some very early results. For example, here we have the 2-photon emission spectrum from gallium arsenide sample with the second harmonic at 525 or so. We were using a 1050 nanometers excitation and fluorescence at 870 nanometers. A 2D image of a sample of gallium arsenide, knife edge measurement. So this is done to characterize the microscope and retrieve the resolution of a microscope based on the thickness, the full width half maximum, and the difference between the theoretical expected curve and what our experimental data, and of course the nonlinear power dependency between our 2-photon signal and our input power. That's it. So yeah, in conclusion, I presented a broadband laser system based on a VCSEL with intrinsically high repetition rate. We believe that the beneficial application in high speed. We believe that this high repetition rate for nonlinear imaging presents some advantage, especially when it comes to mitigating the risk of photoinduced damage. And we're using a pulse shaper to compress multiple channel to the transform limited time duration, or to tailor the spectral phase to any arbitrary function. What I say, tailoring the spectral phase to any arbitrary function, what comes to mind is PUM probe or CAR spectroscopy. For example, so by applying a periodic spectral phase to our incoming beam, we can artificially split it and create some delay between split the pulse and have a variable delay between the two pulses without the need for a translation stage or anything like that. So it has some for single beam cars, for example. So cars will be between two different groups of wavelength, or for PUM probe setup. We can do that without the need for a translation send and beam splitters. The limiting factor for that kind of application would be the spectral resolution of the spatial light modulator. We have a fairly broad spectrum, 350 nanometers or so, that's being spread out over 640, I think, pixels on the spatial light modulator. So our spectral resolution is kind of limited, and we are limited by how high the frequency of that spectral phase periodic function we can add to our beam. So in our current configuration, we can get 100 femtosecond or so a delay between the two pulses, but there's room for improvement. But it will come at the price of reducing the bandwidth, unfortunately. I have actually a very short video just to show that capability. So this is an autocorrelation, and I'm applying a periodic spectral phase function to my beam, and with increasing frequency. And we see the split, the beam split in two and appear as three peaks on the autocorrelation as is expected. So there's possibility to use dynamic spectral masks to do those kind of application. Future work would include multi-contrast imaging on biological sample as well. I showed some very early results with gallium arsenide, but we want to do some result on biological samples as well. So yeah, that concludes my talk. Thank you for your attention. And if you have any question, I'll do my best to answer them.
Okay, thank you very much, Thibault. So are there any questions from the audience at this point? Yep. So I just had a comment. I mean, so it's really nice results, but the pulse duration is quite short. So it's sub 100 femtoseconds, sometimes sub 50 femtoseconds. When you go through the microscope, all the optics tend to distort this, and the pulse duration gets a little bit broader. But presumably with your MIPS, you can pre-compensate for this, right?
That's true. It would require to know what the dispersion going for the optic will looks like, or it would require to get so in how the MIPS looks. So we generating the signal with a BBO crystal. It would require to capture that light after it's transmitted to that optics. So you can do it if you know what the dispersion is, you can preemptively compensate for it, or you need to generate the signal harmonic after the beam is transmitted through that optics. But yeah.
Okay, good. Okay, so we'll conclude this session now. Thank you very much to all the speakers and to the audience for some really interesting questions as well. And see you soon. Bye.
Thank you.
Thank you.
Okay, so I think we can now take a break before moving to the session 3 on frequency comb and semiconductor laser application. So David, you are here, right?
Yes.
Yeah. So you are asking to start, yes, on time, right?
Yeah.
Okay. So in such way, so we just take 5-minute break, and we start as scheduled at 3:15 p.m. For us. Okay. So Maria Angela, maybe you can check.
Hi.
Hi.
Yes. Let me check if all the speakers are present. It seems so. So the second talk is from Nicola Opachak. Are you there?
Yes, I'm here.
Okay, fine. Then we have a talk from Polytechnique University of Madrid, Clara Quevedo.
Yes, I'm here.
Okay. Then Joël Azan.
I'm here. Can you hear me?
Yes, sure. Then Lars Nielsen.
I'm here.
Okay, good. And the last one is Pierre Didier.
Yes, I'm here.
Okay, good.
Okay, good. So everybody is here. So just so we start in 5 minutes. Okay.
Recording stopped.
Oui, je viens de lire. Et quand même, je dois faire le rendez-vous avec elle.
Oui, oui. On peut dire que tu pourras dire j'ai envoyé mon manuscrit le lundi, ça avait été déjà validé. Donc, quand tu prends le temps, au bout du fait, les rapporteurs doivent envoyer leur rapport, il faut bien passer la date de lundi. Quand tu vas la voir, quand tu vois le doctorat.
Pour le lire, que commencer depuis lundi.
C'est ça. Et le manuscrit, j'ai envoyé le 20 parce que mes rapporteurs étaient confirmés.
En fait, que pour connaissance, les process, les rendez-vous, c'est pour quoi? C'est en fait.
Après, il doit signer un papier. Moi, c'est pour la désignation des rapporteurs.
D'accord.
Elle va rentrer dans la Zoom, elle va valider.
D'accord.
Yeah, so David, if you want, you can share your screen.
Yes, I also remind you. Okay, we see your screen now. Okay, it's fine.
You see the full version, not the.
Yeah, we see the presentation mode.
Okay.
Yeah, I think we can start.
Recording in progress.
Good afternoon to everybody. I'm glad to chair this session this afternoon, and I'm happy to introduce the first talk, which is an invited talk from Professor David Burgos, and the talk is on frequency modulated comms in quantum cascade lasers, origins and opportunities.
Okay,
Yes.
well, thank you so much for the introduction, and I'd like to thank the organizer of the conference for inviting me. So today I'm going to be talking about frequency modulated combs and quantum cascade lasers, which is a topic that's grown in popularity over the last few years. But much of my work is also going to be somewhat general to semiconductor lasers more broadly. So, well, if you think about a frequency comb, the basic definition of a frequency comb is a light source whose lines are perfectly evenly spaced or periodic in time. So traditionally, these are based on mode-locked lasers. And in a mode-locked laser, you have all of the lines of the comb in phase with each other. And that's produced by a saturable absorber inside the laser cavity. But it turns out that quantum cascade lasers and actually also many other semiconductor lasers form linearly chirped FM combs on their own without a saturable absorber. And this is kind of what I'm going to be focusing in on today. And so what these linearly chirped FM combs look like is their output looks more like this. So the intensity is mostly constant, whereas the frequency is chirped. Whereas in the other case of the mode-locked laser, the frequency is mostly constant and the intensity is pulsed. So what I'm going to hope to convince you is that this basically represents a new fundamental comb state that is in many ways the opposite of a soliton. Okay, to give you a bit of history on this, combs and quantum cascade lasers have been kind of mysterious for a long time. There's been hints for decades actually, but the problem has always been phase measurements. So if you have a comb that is not a pulse, it is very difficult to measure the phase, at least historically. And the reason for that is that spectral measurements give you no phase information. So if you are trying to do phase retrieval without an optical nonlinearity, you cannot do it without a slow DC detector. So this is the challenge for low intensity combs. What you actually need is you need an AC phase retrieval scheme in order to measure low intensity combs. And so there's been a lot of work on developing this, first by Jerome Faith's lab. They developed a technique called beat node interferometry, which measured some temporal information. And probably more recently, there's been a lot of work using this Swift spectroscopy technique that I developed a few years ago as a postdoc. And what it basically does is it measures the frequency-dependent phase differences, or in other words, just the group delay. So this turns out to not be a great measurement for pulses, but it turns out to be very nice for FM combs because it basically tells you how each line in your comb is related to its neighbors. And the first time this was done on terahertz QCLs, this was done on a lot of messy gain media, which had multiple peaks. And so what you end up with is this semi-boxcar modulation. So your intensity is not a pulse in this case, but the frequency has a boxcar profile, so effectively as it switches between the different sides of the gain medium. But actually, it turns out that if you have a clean gain medium with only one peak, the dominant mode of operation in QCL combs is linearly chirped FM. So again, this was first done by Jerome Faith's lab. And what you see in these combs is that they have a semi-constant amplitude and a linearly chirped frequency. Now, when I say semi-constant, what I basically mean is not nice pulses, not well-defined individual pulses. They tend to have lots of this modulation, and they also have this effect, which is the signal to noise of this tends to be low. So I'll get back to that later on. And to start with, this was somewhat mysterious and maybe even, I would say, controversial, in part because it was theoretically unexpected. So as far as I know, nobody had predicted, especially this mode of operation in one of these lasers. But it turns out to be the case that this is not just a QCL phenomenon, but this is also fairly general. So this has been observed in many different kinds of lasers, especially semiconductor lasers. It's been observed in interband cascade lasers, quantum well lasers, quantum dot lasers. Actually, I think the first evidence for this was published actually quite a bit earlier in 2009, where this is not a Swift measurement, but that they used essentially a series of filters in order to measure, and a fast photodetector in order to measure the frequency-dependent group delay. And for all of these, you get this linear behavior. So, this somewhat implies this should be a fairly universal phenomenon. And if you want to look at the frequency range, this has been it's been over a huge frequency range, almost 2 orders of magnitude. So it's not it's necessarily specific to one kind of laser and one specific process. So it sort of implies that there should be a general description. Now, if you compare this to AM combs or pulse combs, they're very, very well understood. Of course, a passively mode-locked laser, you can describe that by what is basically a Schrodinger equation with a nonlinear amplitude potential. So every change per round trip is governed by a term relating to the gain curvature, which acts as a momentum term, a term relating to the saturable absorption, which is essentially a nonlinear potential term, nonlinear in the intensity, and then the gain minus the loss term, which acts as a source term in this case. By contrast, Kerr microresonator combs are another type of frequency comb. They have completely different physics, but actually more or less the same math. So in this case, there is a momentum term that is related to the dispersion of the cavity. There is a nonlinear nonlinear potential that is related to the intensity that comes from the Kerr nonlinearity, and then also a source term. So both of these have momentum, nonlinear intensity potential term, and a source term. And the solution to this is very famous and is very well known, and that is the Seach solution, which is also known as a soliton. And what we're really trying to get at is whether there is an FM equivalent to this. Is there a toy model that actually describes an FM comb similarly? So, okay, great. But why is this, if there was one, why hasn't it been seen before? Why wasn't it predicted? Well, the issue is that, you have your gain medium inside your cavity. This is a Fabry-Perot laser. The light is going to be governed by Maxwell's equations. The gain medium is going to be described by a 2-level system, at least in the simplest case. Those are the block equations. You glue these together, and what you get is the Maxwell block equations. Now, a Maxwell block equation is essentially completely descriptive. It's at least for a couple differential equations in space and time. You have the electric field traveling in both directions, and you have the population inversion and coherence. And this is basically correct, at least for most lasers. Of course, you can add additional terms. You can add lots of different effects, but this is the simplest version that could actually predict a laser, as far as I know. And the challenge, of course, is that it's very hard to analyze. And if you just write all of the equations down, they're fairly complicated. They're coupled nonlinearly. It's hard to make heads or tails of it. So, okay, well, this doesn't really bode well for finding a simple solution, but you can do a numerical solution, and that has been done by many different groups and many different papers. Here's an example for a quantum cascade laser. So I'm going to show a lot of these types of plots. I'm plotting the intensity on the left, and I'm plotting the phase on the right. The blue curves are traveling in the positive direction. The red curves are traveling in the negative direction. And the intensity for most lasers looks something like this, where the field is growing exponentially inside the cavity and then crashing at the facets where it leaves the cavity. So that's, of course, must be the case. It still balances out, right? Because if you're above threshold, then it should be the case that your gain is balanced by your losses, of course. For an FM comb, the frequency is the derivative of phase. So a parabolic phase will give you a linearly chirped frequency. So that does work, but in some sense, this is dissatisfying because you don't really understand why the chirp has this value. and you don't have a nice way to predict it, at least without just doing another simulation. So in order to understand the physics and the scaling laws, it would be nice if you could actually get this really fundamental description. And so kind of the main goal here is to get these Maxwell block equations down to this one equation. So this has actually been I would say, a fairly slow process by a few groups. The first big step in getting to that result is the development of the adiabatic master equations by Nicola Opepek and Benedict Schwartz. Nicola is speaking after me. And basically the idea here is that you can eliminate the population and the coherence from the Maxwell block equations just using a slowly varying envelope. So here's a simplified version of it. So on the left-hand side, you have the traveling wave component. And on the right-hand side, you have all these terms, the loss, the dispersion, gain and gain curvature. And really, I would say, well, what I refer to as this cross steepening term. So this is really what I would argue is critical for comb operation, because this is actually going to, we'll find out that this actually is going to be the culprit in generating FM combs. Without this, any FM behavior will prefer to dissipate. And this is ultimately from the time variation of the gain grading in the cavity. And so this is a large step forward. It's a very nice result. But in order to get to this simpler version, we wanted to take it even one step further than this. And to do that, we were inspired by this notion of the Lugiato-Lefebvre equation. So if you don't know much about microresonator combs, in microresonator combs, they are usually described by something called the LLE, or Lugiato-Lefebvre equation. And this is the thing that I showed before, the nonlinear Schrodinger equation for microresonators is basically a simplified version of this. And the idea here is that you have in any nonlinear cavity, if the field does not change much within a round trip, you can replace many small time steps with a single large time step, which can be either a round trip or even many round trips. And so this is really nice for simplifying the result because it gets rid of this traveling wave component that I referred to before. So this actually requires that you take a time step for each position in your mesh, whereas doing a mean field theory doesn't actually require that. But the problem is, this turns out to be a really bad approximation for Fabry-Perot lasers. So the requirement for this mean field theory to work is that the field should not be changing much inside a round trip. And of course, in a Fabry-Perot laser, the field changes a lot within a round trip. This exponential gain, I would call that large. The crashing at the facets is also very large. It's actually delta function-like if you think in terms of losses. So this isn't going to work, well, at least not directly. And so what you have to do is you have to take a series of steps in order to convert these master equations into a mean field theory. So I'm not going to go through the details. You can refer to this paper if you want the details. But basically, the idea is you start by flipping the field around. So this is an artificial extension of the cavity. So you flip the negative waves and basically glue them to the positive waves. And so when you apply periodic boundary conditions, your field now appears like it's moving in one direction. You then normalize the field to its CW power. So if you look at this power increase inside the cavity, this actually basically closely mimics the CW power of the laser, which again is exponentially increasing and then decays at the facets. So when you do that, your intensity now appears to be somewhat constant. And now your intensity and your phase are basically traveling in one direction, and they're not changing very much. And so the result of that is that you can actually average. So you can apply this mean field theory. And when you do that, your wave basically now appears stationary, at least over a few round trips. If you look over longer periods of time, the wave will actually slowly evolve. So kind of here's the high level view of this process. You start with the Maxwell block equations, which is 4 equations. You reduce that to the adiabatic master equations, and you do this procedure, and that takes you down to the mean field theory. By the way, I should mention we call the normalized field, we denote this by F. So when you see F here, this is referring to the normalized and extended electric field. So it's one field now, but it's effectively, you can think of it as electric field. Okay, so what do you get when you do that? Well, the result is still fairly complicated. I'm not going to go into too much detail here, but basically there are the most important terms are shown here. First, you have the dispersion and the gain curvature. You have a term that is restoring your amplitude to a constant level. And then you have this cross-steepening term. Unfortunately, if you look closely, some of these terms here involve a convolution. So you, especially the cross-steepening term and one of the amplitude restoring terms. And so this is still fairly difficult to analyze, at least analytically. But you can analyze this numerically a little bit easier with the split step method. So that's kind of nice. And you can easily modify this for various, to include various physical effects. So if you actually just do this for FM comb, for nice linear FM combs, you actually get something that is reasonably predictive. And you can, if you do this for these previously mentioned boxcar combs that we saw in these double peak gain media, it also reproduces those. So that's kind of nice, but it still doesn't get us to where we want to go, which is like something simple that we can wrap our heads around. And to do that, you have to take this process one step further, and that is to assume a constant amplitude. And what we're going to find is that this actually takes us to something which is very analogous to the nonlinear Schrödinger equation, but is not in terms of intensity, but is in terms of phase instead. So whereas this mean field theory was actually involved convolutions, so it was a little bit hard to think about, this final version is a differential equation alone. So when you do that, this is what you get. So you find that the field of the FM cone is described by this nonlinear Schrödinger equation. Probably the most important term is this phase potential, because this phase potential term is going to cause the phase inside your cavity to amplify. And this is actually going to allow you to generate the FM. Of course, there are some other terms. There is a group velocity dispersion term, which is second derivative, of course. And then there's also a source term. And the source term is going to set the amplitude. So there's also a gain bandwidth component, which we'll ignore for now, but this is essentially the simplest version. And this is something that you can actually solve analytically. So where does this phase potential term come from? It's a bit subtle. You actually have to follow the derivation in detail. But basically what it comes down to is it comes down to a combination of this cross-steepening nonlinearity and the mirror losses. So this cross-steepening nonlinearity, as I mentioned before, it comes from the time variation of the standing wave. So if you have a single mode laser in a cavity, your single mode laser, the standing wave is going to basically be constant. It's going to stand. But if you have something that it has many components, this will not be the case anymore. The standing wave itself will move. And so, for example, in an FM cone, the standing wave looks something like this. What happens is that you get this reflection from the gain gradient, and it changes very quickly when it hits the facet, and there's a large mirror loss, or in other words, small reflectivity. And this leads to this phase potential term. So you can think of it as ultimately it's a non-instantaneous chi-3 nonlinearity. So it's a nonlinearity that is proportional to, well, basically a wave, but also it's the time variation of the wave that's propagating against the wave you're considering. So, okay, so I say we can solve this analytically. What does it look like? Well, to do this, we'll kind of compare this to solitons. So if you compare this to solitons and microresonators, or otherwise I'll refer to them as AM combs just because that's easier to say. They are governed by a nonlinear Schrodinger equation with an intensity potential. FM combs are governed by the same thing with a phase potential. The analytical solution in the case of a microresonator is a SEACH. In the case of an FM comb, it turns out to be a chirped, chirped, I guess you can call it a chirped Gaussian, but it has a constant amplitude and it has a phase which is parabolic. You can actually also get the carrier envelope offset from this. If you compare the potential, in this case, the potential ends up being kind of the opposite of the SEACH. So it has this well shape, and in this case, the parabolic shape. You look at the intensity of a soliton, it's peaked and then has a constant frequency, whereas FM combs have constant intensity, but chirped frequency. So these waves are completely localized. These waves are actually completely delocalized. In fact, they have to be completely delocalized for reasons I'll get into in a bit. So these are normally called solitons. Actually, originally I wanted to call these phase solitons, but several reviewers thought that was not appropriate because they are spatially extended. So we've been calling these extendons. So, all right, yeah, okay, we made a bunch of approximations. Does it actually work is the next question. You can compare this to more sophisticated, numerical calculations, and you find that in fact, actually it does work very nicely. So basically, if you look at the intensity is mostly constant. I'll get back to this in a second. The phase is again parabolic with the curvature that was predicted by the theory, and the frequency is also chirped with an amount basically predicted by the theory. The big discrepancy is here at the boundary. The theory actually breaks down here because the form that we solved for actually was discontinuous here. So what you find is that you actually get this little mini, I don't know what to call it exactly. I don't think I would call it a soliton, but you get a little mini perturbation. We'll call it a perturbation in the intensity, where the frequency jumps back in the other direction. And actually, this, if you remember, has been observed in experiments several times, actually, although the signal to noise tends to be not great. So if you think about this in the frequency domain, so all this is in the time domain or the spatial domain. In the frequency domain, the spectra look more or less flat. You can think of this as the frequency sweeping across. So that's kind of nice. So this is one possible solution. It turns out there's actually other solutions as well. So if you initialize this field to here, let me reset that. If you initialize this field to something which is periodic in the round trip frequency, it will actually converge to this case where you have multiple extendons per round trip. So the intensity, again, looks mostly constant. The phase now is broken up. It has the same curvature as the fundamental case, but it only sweeps, in this case, half as much because it's divided up into two inside the cavity. And you can do this for an integer number of any integer number, essentially. And this spectrum is going to basically have holes in it. This one will have a hole every other FSR. And if you're familiar with QCLs, you actually know that this is something that's been referred to as harmonic states. So a harmonic state, these have been observed experimentally many times, and they actually also have this linearly chirped FM associated with them. So you can actually think of these as being analogous to higher order solitons. So, okay, I promised that what's nice about this is that you can actually now calculate scaling laws. And so if you put this in terms of physical parameters, the total FM bandwidth is basically something like this. This is as simple as I can make it. So as many approximations as possible, that actually is reasonable. And what you find is that at least for this model, what you get is that the chirp bandwidth is going to be proportional to the mirror losses. So mirror losses are very important. It's going to be proportional to the round trip small signal gain. It's going to be inversely proportional to the group velocity dispersion, and it's going to be proportional to the upper state lifetime of the laser due to this cross-steepening nonlinearity. So why is this mostly observed in semiconductor lasers, or in particular Fabry-Perot lasers? It's because of the mirror losses. It's much harder to get an FM cone if you don't have high mirror losses. So if you have a ring laser, ring lasers tend to have very small mirror losses, so it's harder to form FM cones. For solid state lasers, again, you have the situation where the gain medium is not really filling the cavity. This works better for light that fills the cavity. So this is not usually going to observe FM cones. But Fabry-Perot lasers, well, especially if they're cleaved lasers, are very nice because they tend to have really large mirror losses, which of course also helps you couple power. But they also, as a side effect, give you these FM cones. Now, there's one thorny issue. That is the group velocity dispersion. So the group velocity dispersion, if you have 0 GVD, this formula predicts infinite cone bandwidth. And of course, that doesn't happen, right? Because that's impossible, right? And that is because we ignored the gain curvature aspect. The gain curvature is going to really affect this. If you exceed the bandwidth of the gain medium by trying to make this too small with too small dispersion, then the intensity of the wings will start to drop because you'll be sweeping over more than the gain bandwidth can really support. All right, so well, what's the effect of that? Well, if the intensity drops, it turns out this is going to destabilize the cone. So, you know, if you just run the same simulations, what you find is that basically the red curve here is the theory. The blue curve is the numerical version, and you find that it just kind of oscillates semi-periodically. So basically, if your intensity starts to drop too much, your cone destabilizes and the whole thing falls apart. So this is one reason why you can really call these, think of these as extended waves. They really cannot be localized in order to be stable. So then specifically here, the constraint is that the intensity cannot drop by more than some fraction before this actually starts to happen. So in conclusion, I discussed how FM cones are a fairly universal phenomenon for QCLs, but really semiconductor lasers more broadly. You only need a few parameters in order to describe them. Explains their apparent ubiquity. You know, you can think of this as really being closely related to the mirror losses. The solution is a nonlinear Schrodinger equation that obeys a phase potential. It also explains harmonic states in a nice way. And of course, you can use this for other sorts of cones. If you want to include satchable absorption, you can include, you can do it for multi-level lasers, you can include line width enhancement factor, many other terms if you want. So most of this code is online, and I would like to, again, thank you all for your attention, and would appreciate any of your questions.
Okay, thank you very much. Very interesting. Are there any questions from the audience? Please, you should raise your hand to ask questions. No? Okay. We have one question from Mikhail Belkin, please.
Thank you. Hello, David. Very nice talk. Thank you.
No.
I was wondering, you mentioned that you had this sort of final equation. There you mentioned, first of all, that rings would not produce combs, ring lasers.
They won't produce this kind of comb in general, at least not unless, well, I mean, I guess it depends on really what sort of mirror losses you can make in your ring.
Right. I'm just wondering because there were reports of ring lasers that QCL's ring lasers that produced comms.
Yes, they don't produce FM comms.
So these are not FM comms.
Yes.
Okay. And a second. Okay, so I have not seen the analysis. I somehow assume that it's the same type of comms, but you're saying they are not. This would be some soliton.
Yeah. So those combs, you know, I wouldn't say there's a, as far as I know, there's not a nice way of describing them. So they don't have this clean FM profile, but they also are not solitons exactly. So they're probably, you know, there's something in between. So they're described by you know, basically a similar. So if you take, actually, it's almost the same equation, but if you remove the phase potential term and add some other terms as well. So as far as I know, there's not a nice analytical description for those kinds of combs, at least not yet. There might be going forward though.
Okay, thank you. And one other small question regarding your final equation. You have this expression for the net gain, and you subtract mirror loss and waveguide loss in that final equation. So what is left? It's a naive question.
So this is. So you mean after, okay, so this is the small signal gain minus the, so this is the, so above threshold, sorry, to clarify, this is the small signal gain. So this is what the gain would be if there was no light inside the cavity. So what you're thinking about is above threshold, the gain, if this was gain minus waveguide loss minus mirror loss, then that would be 0, right? But the small signal gain can be as high as it wants to be effectively.
And do we have time? Because I'm still puzzled with that.
I think you can continue the discussion after.
Okay.
Yes, because we are running out of time, and I see there's still another question from Edgar Fernandez, please.
Yeah, so thank you very much for the presentation. I have a general question about these AM and FM comms, about the applications that we can consider for them. Is there some application where FM comms are better or they have some advantage? Or
so one nice aspect is that, and well, first of all, you can turn an FM comb into an AM comb. If it's nice and linearly chirped, then you apply a linear chirp in the opposite direction, and now you can have an AM comb from your FM comb, just using passive means. But for applications like spectroscopy, especially, actually having an FM comb can be beneficial because, you know, if your goal in spectroscopy is usually to make your signal as large as possible, having a pulse is going to be more easily saturate your detector and create sorts of nonlinear artifacts. So, you know, having an FM is actually beneficial there. Now, you know, for nonlinear spectroscopy, obviously an FM is going to be not as good, right? But the other thing I will say is specifically in QCLs, it is very challenging to make a pulse in general. So there was a recent report of that from ETH, but you know, there's been a lot of work in attempting to make like nice passively mode locked mid IR QCLs, and that has never, as far as I know, hasn't ever been as competitive as something like a solid state laser, let's say. So in many ways, you're kind of limited to FM combs due to the gain recovery time of the laser.
Okay, Thank you very much. It's very intriguing. It would be nice to continue this discussion, but we have to move to the next talk. I'm glad to introduce the second speaker, Nicola Opachak, with a talk entitled Measuring the Line Width Enhancement Factor During a Frequency Comb Operation. Please.
Hello, can you hear me?
Yes, we hear you well.
Great. Let me share the screen.
Okay, it's good. It's in presentation mode.
Okay. So thank you for the introduction. I'm happy to share with you today our latest findings and the novel measurement technique of the line width enhancement factor in a multimode semiconductor laser frequency comb. So semiconductor lasers are nowadays widely spread in our daily lives and also modern technology. Their main benefits over other laser types are that they are electrically pumped, they have a broadband gain, and also they are very compact, which allows integration with other.
Nicola, sorry to interrupt you. You are not in the presentation mode in the shared screen.
Am I not?
No, I see it in presentation mode.
Okay. Yeah.
I also see it well in the presentation mode.
Yes, it's presentation mode.
Oh. Yeah. Okay. So, Benedict, are you only the one who has a problem, or?
Then please continue.
Okay. Thanks. So their main applications include telecommunications, then ranging, for example, in autonomous driving, and also, of course, high precision spectroscopy, just to name a few. Therefore, it is absolutely crucial to understand their working principles and also the parameters that will allow any kind of future advances. So one of such important parameters, which is also recently gaining a lot of attention due to its role in frequency comb dynamics, is the line width enhancement factor. Originally, it was introduced to explain the broadening of the laser line width beyond the shallow Towns limit in semiconductor lasers. So in other laser types, the lasing transition is very sharp, but this is not the case in semiconductor lasers, where the levels are much broader. The line width enhancement factor itself is defined as the ratio of the carrier-induced changes in both the real and imaginary part of the refractive index, which as a consequence means that the line width enhancement factor describes the coherent coupling between the amplitude and the phase of the laser light. This is absolutely crucial for frequency comb dynamics, and it can lead to the formation of FM combs, which David was explaining in the previous talk, and even in solitons. So the line width enhancement factor has been studied since the 1980s, and yet the existing measurement techniques have several drawbacks. Most of them rely on the emission of single modes, and they are limited to near or sub-threshold operation. So this means that if we would have a technique, it would be amazing to have a technique which can work for arbitrary laser sources and arbitrary laser biases, a technique that can also directly work for multimode operation and also measure the line width enhancement factor for each mode in the laser spectrum. And since we already made quite some goals, the technique should also be fast. Okay, so we can start from the theoretical description of a modulated single mode laser. When we apply a modulation to the bias of a semiconductor laser, we simultaneously modulate its intensity and also its optical frequency, as can be seen in this equation, where F mod stands for the modulation frequency. Here, the parameter M describes the intensity modulation, and the frequency modulation is given with the parameter beta. Additionally, 5 describes a general phase shift of the entire signal, and theta describes the phase shift between the intensity and the frequency modulation. For an intuitive picture, this is represented in this figure here, where you can see the sinusoidally modulated waveforms of both the intensity and the optical frequency of a single mode laser. Now for us, this is of special interest because the limit enhancement factor can also be defined as the ratio of these two modulation indices. So let's analyze this a bit different now. You can see here the spectrum of a single mode laser. And when we apply a modulation bias, we create modulation sidebands, which are here denoted as E- and E+. They are separated from the central mode, of course, by the modulation frequency. Now, all of this happens in the optical domain, but these sidebands also interfere with the central mode and create beatings in the RF domain. They are here denoted with B- and B+, and of course, they lie exactly at the modulation frequency. Mathematically, we can describe these beatings in the following way. And after some lengthy derivation, we can also link them with the modulation indices beta and m. Now, comparing these two equations with the original definition of the limit enhancement factor, we can arrive to a new formula, which allows us to calculate directly the limit enhancement factor from these beatings. In order to verify this, we first conducted some numerical simulations. We employed a spatiotemporal model, which is based on the Maxwell-Bloch formalism, and which additionally includes the value of the limit enhancement factor at the gain peak in order to describe the gain asymmetry in semiconductor lasers. So we simulated a single mode laser, which we modulate, and then using our newly derived formula, we calculate the limit enhancement factor at the lasing frequency as we tune it around the gain peak in discrete steps, which are here indicated by these markers. The gain peak itself is a zero frequency, and we do this for 3 values of the limit enhancement factor at the gain peak. So again, these markers represent values that are calculated from the simulations, and the solid line gives the analytic model for the limit enhancement factor. We can see that they are basically in excellent agreement, which is already a very good sign that we are on a good path. However, so far we analyzed only single mode lasers, and our wish is also to be able to measure multimode lasers. Luckily, the same method is still valid in this case, and we can arrive to the following picture. These blue lines represent the multimode laser spectrum, and then we again apply the modulated bias to create these modulation sidebands. They interact with their central modes and create beatings in the RF domain, and using them, we can calculate the limit enhancement factor similarly to the case of a single mode laser. However, now the difference is that we calculate one value of the limit enhancement factor for each one of these modes. Experimentally, this is conducted by applying basically a frequency discriminator in the form of a narrow bandpass filter, and we scan it across the entire spectrum. So we wanted, again, to confirm this first on a numerical simulation, but the goal is now to aim for frequency comb operation. You can see here the intensity spectrum of a frequency comb, and using the formula that we previously derived, we are able to calculate the spectrally resolved LEF. This is shown here on the plot below, where the red markers indicate the limit enhancement factor, which is calculated for each comb mode individually. The blue line gives the analytic model, and again, you can see that there is a very good agreement. The slight deviation at the spectral edges is attributed to coherent coupling between these modes. Okay, so now for the interesting question, how can we actually apply this technique and measure the spectrally resolved limit enhancement factor of a real device? It turns out that we can use this very elegant technique that David was also mentioning in the previous talk, It's called SWIFTs. And using it, we can detect the beating signals of every mode in the laser spectrum. And furthermore, we can also detect the amplitude and the phase of the beatings. So I'm going to go a bit more into detail now. The centerpiece of our experimental setup is the Fourier transform infrared spectrometer, or the FTIR. It consists of a movable and stationary mirror and also a beam splitter. At the entrance, we place our laser source, which was a QCL, quantum cascade laser in our case. Using a bias T, we drive it both with DC current and an RF signal. Then the laser light is passed through the FTR, and the interferometric signal is measured by a very fast quantum well infrared photodetector, which was optimized for RF frequencies. High RF frequencies are needed because we need to create a sufficiently large spacing between each mode and their bit nodes. This is necessary for the FTR to be able to actually detect these individual bit nodes. After that, we use a low noise amplifier to boost the signal, which we then down mix to megahertz range with a local oscillator. This allows us also to use a lock-in amplifier to increase the signal to noise ratio even more. And as a reference, of course, we use the original RF signal. Now, finally, we perform a scan with a moving mirror. We record the interferometric signal to the Fourier transform. And from it, we have both the amplitude and the phase spectrum of the beatings, from which we can calculate the limit enhancement factor for each mode in the laser spectrum. So finally, we arrive to the experimental results. You can see here the spectrum of a frequency comb with the highlighted gray area, which we zoom on the right. Again, on the top, there are comb modes. Red, we show the amplitude of the beatings, and below you can see their phases. According to the formula that we have derived earlier, we can now use this information to calculate the limit enhancement factor for every mode in this spectrum. And this is exactly what's displayed in the plot below. The red markers show the limit enhancement factor that is extracted from this measurement. And you can see that its shape follows nicely the analytic model and also agrees with the previous simulations that I showed. Furthermore, the values of the limit enhancement factor that are reported are in good agreement with the literature. It turns out also actually that from the same measurement, you can infer the saturated value of the laser gain width, but this still remains to be a topic for some future research. So this already brings me to the conclusion of my talk. We have here presented a novel technique to measure the limit enhancement factor, which we first verified using numerical simulations and then experimentally demonstrated on a real device. Our technique fulfills all of the requirements that I have said in the beginning of my talk. It works for arbitrary laser sources and biases. It is the first technique that is able to work directly on a multimode laser, and hence it measures the limit enhancement factor, which is resolved over the entire laser spectrum. And lastly, it is also quite fast since it relies on a single shot measurement. So with this, I would like to thank my colleagues, the funding agencies, and of course, you for your attention. Thank you.
Thank you a lot. Are there any questions? Okay, we have a question from Hans-Peter.
Yes, very nice technique. But in your say expectation, it's a rather long list. I'm wondering if you say it's arbitrarily bias can be used for extracting the linear enhancement factor. So how much? So if you go to high bias level, you are not too much disturbed by nonlinear phenomena, in particular maybe 4-wave mixing and these kind of effects.
Yeah, okay, so in order for the technique to work, the laser must emit a frequency comb. And for this particular purpose, four-way mixing is quite beneficial because it allows easier formation of frequency combs. So particularly this was done for a QCL. And yeah, there it was possible, let me show you, yeah, to measure this for basically the entire range of the currents.
So even if you go deeply into saturation, then
yes,
they're working.
Yes, it does.
Okay, interesting.
Okay, thank you. Another question, David, please.
Oh, yes, very nice result. So my question is sort of kind of what the effect of a frequency-dependent line width enhancement factor gives you, like in terms of, I guess in terms of comb operation. Is there anything that you get from the frequency dependence that you would not get just by assuming that you had a constant value?
Yeah, that's a good question. Well, actually, if you use a constant value in the model or in the Maxwell-Bloch model, that value is only at the gain peak. So actually, the value of the alignment enhancement factor, even if you do that in a theoretical model, looks very similar to this. It's never a constant value. And that's exactly why we think it's crucial to be able to measure how this looks like in real devices, to understand better how this influences comb synchronization. And also, for example, this was measured for an FM comb. We will be interested also to see how it looks like for different types of combs, for example, AM, if it's possible. So yeah.
Thanks.
Frederick, please.
Yes, thank you for the talk. Just a quick question. You mentioned that you have to use a quite high frequency to reach your condition. Can you precise typically?
Yeah.
Okay.
Yeah. So the repetition frequency for this laser was 12.2 gigahertz, and we used the modulation frequency of 9.5. We also built a custom FTR with a resolution of 500 megahertz in order to resolve this very nicely.
And one more question. Do you think with this technique you could be able to predict eventually if the alpha becomes negative?
Yes. So here I have used the absolute values of the sign, but you can actually also infer the sign of the alignment enhancement factor because of the slope. So you have seen the slope of the alignment enhancement factor, and it always needs to be negative. So if you would obtain a positive slope, that means that you need to flip the sign. And this can be proven also analytically, starting from this analytic expression of the alignment enhancement factor. Then when you find the derivative, you can see that it always has a negative frequency. If you're interested more, you can search for this in the supplementary material of the recent publication.
Okay, thank you.
Thank you very much. Let's move to the next talk. We have now a talk given by Clara Quevedo Galan from Polytechnique University of Madrid. The talk is entitled Gain Switched Optical Frequency Comb with Comb Spacing down to 5 megahertz.
Okay,
Please.
Good afternoon. Can you see my presentation and can you hear me?
Yes, we hear you and we see your presentation, but it's not in presentation. No, okay, now it's fine.
Okay.
It's presentation mode.
So good afternoon, everyone. My name is Clara, and this work has been developed by the Applied Photonics Group of Universidad Politécnica de Madrid. These are the contents of my presentation. I'm going to start making an introduction of the generation techniques of optical frequency combs with semiconductor lasers. And in particular, I'm going to explain the technique that we use to generate the combs, which is gain switching. And I'm going to focus on low repetition rate optical frequency combs and their potential. Then I'm going to set the motivation of this talk, and I'm going to show you some experimental results of the optimization of 100 megahertz gain switch combs and experimental measurements of gain switch combs at frequencies below 100 megahertz. And to finish with, I'm going to draw a brief conclusion. Well, optical frequency combs are coherent light sources whose spectra consist of equally spaced discrete tones. And optical frequency combs generated from semiconductor lasers have gained a lot of popularity due to some of the advantages or features that they offer in terms of cost, small footprint, or potential to be integrated, among others. So there are several techniques to generate these combs from semiconductor lasers, and they are illustrated in this slide. And depending on the application, one can choose one technique or another. So for instance, regarding electro-optic combs, some of the features that they offer is wavelength tunability, and also the repetition rate can be flexible modified. But for instance, to get flat optical spectra, one need to go to more complex architectures, for instance, putting some modulators in cascade. And regarding microresonators or mode-locking based combs, they can cover a wide bandwidth, but the repetition rate is fixed since it depends on the cavity length. And as I have mentioned, the technique that we use is gain switching. It consists in directly modulating a semiconductor laser with a large amplitude radio frequency signal. And its implementation is quite simple since one needs to superimpose this radio frequency signal to a direct bias current using a bias T element. So if the laser is biased close to its threshold current and it is modulated by a large radio frequency signal, we can switch the laser from below to above threshold, generating narrow optical pulses, which give rise to an optical frequency comb. And some of the characteristics of the combs obtained with this technique is that they are very easy to implement, as I have mentioned. They feature wavelength tunability. Also, the repetition rate can be easily modified. The spectra are flat. They can be integrated in photonic circuits, but on the other hand, they offer a more reduced bandwidth than the combs generated with other techniques. And in particular, I'm going to focus on low repetition rate gain switch combs. As far as we know, the lowest optical frequency comb repetition frequency reported using this technique is 100 megahertz. And in previous work, we generated a couple of these combs to perform dual comb spectroscopy, being able to measure a narrow transition whose line width was 2 gigahertz with a very good resolution. And in this case, to generate the combs, we use pulse gain switching with external optical injection from a master laser to preserve the coherence between the consecutive pulses. And in this work, we are going to use the same approach. And as I have mentioned, we are going to focus on low repetition rates, which means that the electrical pulses will have very low duty cycles, and that the main challenge that we are going to face with is the low optical power. So the motivation is the optimization of low repetition rate gain switch combs, since we think they have great potential for applications requiring high resolution, such as high resolution dual comb spectroscopy or dual comb ranging systems, where the lower the frequency, the higher the unambiguous range we can reach. And now I'm going to move on to the experimental results. This is the first experimental setup that we are going to use for the generation of the optical frequency combs. and the measurement of these comms in the optical domain. The experimental setup is based on a master-slave configuration in which the slave laser, which is a DFB laser, is modulated with a train of electrical pulses that are provided by a pulse pattern generator. And the master laser provides the external optical injection, and its wavelengths can be tuned along the telecommunications band. And in the setup, we have included an optical amplification to overcome this low power issue. And the optical spectra are measured in the optical domain using a high resolution optical spectrum analyzer, which is a Brillouin optical spectrum analyzer, a BOSA. And regarding the methodology that we are going to use for the optimization of the comms, we are going to use two figures of merit, which are the bandwidth at 10 dB and the carrier to noise ratio, which is defined as the average of the ratio between the intensities of the comm tones that are within this 10 dB bandwidth and the noise floor between adjacent tones. And we are going to study the influence of the gain switching parameters on the comm characteristics. So firstly, we have performed an optimization of 100 megahertz gain switch optical frequency comms, and we have found out that the parameters that most influence the comm characteristics are those related to the electrical pulses, and these parameters are the pulses amplitude, denoted as VRF, and the pulses duration denoted as tau pulse. The parameters related to the optical injection and the bias current of the slave laser have been found much less influential than these two parameters. So as we can see here in the graphs on the left, we can see that the spectral width at 10 dB follows a linear relationship with the pulses amplitude up to a saturation point around 8 volts peak to peak. And this can be attributed to an increase of the dynamic chirp. And from this point, the quality of the comms worsens, probably due to the excitation of the second spike of the relaxation oscillations. And regarding the influence of the pulses width, we have found an optimum value around 200 picoseconds. And taking into account these two values, we obtain an optimum optical frequency comms for this repetition frequency, featuring a bandwidth of 121 gigahertz and a carrier to noise ratio of 15 dB. And here you can see a zoom of this region of the spectrum. So based on these results, we are going to set these two parameters to values to, the pulses amplitude and the duration of the pulses, to values of 8 volts peak to peak and 200 picoseconds respectively. And we are going to lower the repetition frequency of the comms progressively. So here you can see the results obtained for 50, 25, and 10 megahertz. And as you can see, when we lower the repetition rate of the comms, one cannot longer solve the teeth properly, because the resolution of the instrument is limited to 10 megahertz. So for repetition frequencies lower than 25 megahertz, we are going to use heterotime detection for the measurement of the comms. So this is the setup that we are going to use for heterotime detection. Regarding the comm generation part, it remains the same, but we have added an additional branch in which the wavelength of the master laser is shifted 80 megahertz by means of an acoustoptic modulator. And after the amplification stage, both the signals from both branches, bit in a photodetector, and then the radio frequency heterodyne spectrum is measured with an electrical spectrum analyzer. So at the output of the photodiode, we can distinguish two kinds of terms, which are the direct detection terms at multiples of the repetition frequency, as you can see in here, marked in black, and the optical frequency comb tones. And for a proper reconstruction of the optical spectrum, it is needed to distinguish between the tones located at positive frequencies and the combs tones located at negative frequencies that are folded into the positive part of the spectrum, which are these ones marked in green and in red, respectively. And in addition, the repetition frequency must ensure that there is no overlapping between the harmonics for a proper reconstruction. And in our reconstruction process, we lose the information of the line width of the harmonics, since we just take into account the intensities of the peaks. But still, the main objective of this technique for us is to check that we have well-resolved harmonics that are above the noise floor. So from 10 or 11 megahertz, we reduce the repetition frequency down to 5 megahertz. And here you can see the optical spectrum featuring a great number of comb teeth. And here you can see the radio frequency spectrum measured with the ESA. And once one can check that the peaks are well resolved and the frequency space is the one expected. And to finish with the results, we lowered again the repetition frequency by a factor of 2. And from this point, the low power per teeth becomes more evident, but still with optical amplification, we can say that this comb could be a stage forward to high resolution or megahertz resolution spectroscopy. And we can see that in this case, the duty cycle is very, very low. And to conclude with, we can say that after an experimental optimization, we have obtained wide 100 megahertz optical frequency combs, and that the 2.5 megahertz repetition rate comb could be, as I have mentioned, a first stage towards megahertz resolution dual comb spectroscopy and high resolution dual comb ranging featuring 41,000 tones within 10 dBs. And as the main drawback to overcome is the low optical power, for in the future we will have to research for new techniques to overcome this issue. So thank you very much for your attention, and if you have any questions, I will be very pleased to answer them. Thank you.
Thank you very much. Any question from the audience? Yes, we have a question from Xavier Porte.
Yeah, thanks, Clara, for the nice talk. So I see you use EDFA for amplification. So if you would like to have maybe a integrated system, you would consider probably to use a semiconductor optical amplifiers or so on. So, but then typically maybe the noise figure is not so good. So how critical would be that?
Yeah, that we will be critical. In fact, we are looking for new techniques to, for instance, modify the pulses sequence of the electrical pulses to have to increase the duty cycle and to overcome the power limitation from this side, and to go to more simple architectures without the need of optical amplification.
Any other question? No, I do not see any other question. Okay, let's move to next talk. Next talk is given by Joël Hazan from Technical University of Eindhoven, and the talk is entitled Investigation of the Wavelength Tuning of an Integrated Laser System on Indium Phosphide for Optical Coherence Tomography. Please.
Thanks for the introduction, and welcome everyone. I'm Joël Hazan from University of Technology of Eindhoven, and today I will talk about the investigation and the progress made on the wavelength tuning for an integrated laser system on indium phosphide for optical coherence tomography application. I will start with a brief motivation for my talk. Then I will move on the laser design and the laser design improvements. And then I will show some wavelength tuning measurements, results, then an improved control strategy to improve the tuning speed, and then I will conclude. So starting to speak about optical coherence tomography technology. So OCT is an interferometric imaging technique that allows us to obtain biological tissue images from their reflections. So the schematics here is drawn on sorry. So here we can see a schematics of the OCT setup. So we have an optical input and then a beam splitter divided the beam into two parts. One part is hitting a reference mirror and the other one is catching reflections from the sample. And then when they interfere at the detector through a fast Fourier transform approach, we can obtain the reflections together with the relative position of the reflection peaks. From one scan, we can obtain the so-called A scan, so in one dimension, only on the vertical dimension, and combining multiples of A line, we can obtain a 2D scan, and then combining multiple 2D scan, we can obtain a full 3D imaging of our biological samples, as in this case, an image of the skin of the hand. We now will focus on the requirements that we need to have on our tunable laser source in order to be used as a stepwise scan for an OCT source. So our tunable laser needs to, in order to be used as a source for optical coherence tomography, needs to have a maximized tuning range of around 100 micron at 1.5 of 100 nanometers, sorry, at around 1.5 micron in order to obtain 10 micrometer of axial resolution. Then we want to have 10 gigahertz of spectral sampling interval to maximize our imaging depth of 1 millimeter. And we need to have high output power and high side mode suppression ratio in order to obtain a good signal to noise ratio and make a good imaging of our sample. We want to develop our laser within our indium phosphide integration technology platform and 1.5 micron, in which we have a standardized basic waveguide such as semiconductor optical amplifier, in which we have a quantum wells embedded in the quaternary core layer to generate light. Then we can have electrorefractive modulators to modulate the light, and two different type of etching technology for the waveguide, the shallow and the deep etch waveguide. Combining these building blocks, we can build complex circuits such as in multi-project wafer runs, and we can build more complicated devices such extended cavity lasers that I will talk about in the next slide. So to filter the wavelength, we use an asymmetric Mach-Zehnder interferometers in which we have two arms. Everyone has a phase modulator and we have an arm mismatch. If we look at the wavelength response of this asymmetric Mach-Zehnder, we will see a sinusoidal function in which the free spectral range is given by the arm mismatch between the length mismatch between the two arms. Then if we include this filter inside the ring cavity, then we have multiple longitudinal cavity modes that are spaced by the free spectral range that is given by the length of the cavity. And then we put inside the cavity an amplifier in order to have some gain curve and generate light. If we cascade multiple filters with different imbalances, we can have better and better wavelength selection at every stage in order to have a single mode laser filtering only one single longitudinal cavity mode. Then we tune the laser with applying reverse bias voltage to our phase modulators in order to obtain an athermal tuning and make the thermal effects during the tuning negligible. This laser was already developed and found a record of tuning range of 74 nanometers centered at 1550 in the measurement. We now want to design new laser in order to improve the performance and moreover to improve the tuning range. So we included another Mach-Zehnder modulator that we'll use as a variable outcoupler in order to increase the tuning range. We revised the imbalances of all the filters to get higher side mode suppression ratio, and we make the cavity shorter in order to have wider longitudinal mode spacing. So I would like to focus on the variable outcoupler first and how does it work. So we apply voltage on the two arms of this balanced Mach-Zehnder modulator, and we can tune the outcoupling fraction of this laser. And most importantly, we can tune the intracavity losses inside. And as a consequence, we tune the tuning range because we increase the current density that is needed on the SOA to achieve the threshold of this laser. So for example, if we change the losses inside our cavity, changing the outcoupling fraction from 50 to 75%, we are increasing the losses of 3 dB, and we end up in a different gain curve at threshold. In this way, the gain bandwidth is enlarged. So for instance, if we look at the gain curve at 3 kilo per centimeter square with respect to the gain curve of 4 kilo per centimeter square, we obtain an increase in the gain bandwidth that is the first limitation to our tuning range, and so in this way we can enlarge it. This is a picture that shows the realization of the laser. I highlighted the dimensions because we also want to have an integrated chip, so having a very small footprint. And this laser is in total 3.5 times 0.45 millimeters, and we put it inside a package in order to have three main advantages. So with the thermistor and with the cooling element through a Peltier effect, we can control the temperature of the substrate and more or less stabilize it. Then we glue a polarization maintaining fiber to maximize the output power, and we can have a PCB to easily access all our 8 control settings inside the filters. We measure the package laser through an array waveform generator with 8 channels that supplies voltages from 0 to -8, reverse bias to the tunable laser that is packaged, and the temperature is fixed to 16 degrees, and the current on the SOA is fixed to 150 milliamps. In this way, we can obtain laser spectra from the optical spectrum analyzer with 10 picometer resolution, and here is an example of the spectra in which we can see the feature of all the 3 filters and a lasing peak. By varying the voltages over the 3 filters and the variable outcoupler, we can then achieve our goal to enlarge and enhance the tuning range with respect to the previous laser design. So now we have a tuning range of 90 nanometers, and together here on the right with a nicely high output power. And here is plotted the lasing wavelength as function of the coarse voltage. Of course, for every coarse filter voltage, we have a very large number of lasing spectra. The problem of this measurement are basically 3. So first of all, we don't have a uniform wavelength step over the whole range, as is required for optical coherence tomography. This measurement takes a very long time, so between 2 and 3 days, and the reproducibility of this wavelength is a problem. So we have less than 50% of reproducibility after 3 weeks within 12 gigahertz accuracy, and that's not ideal because we want to calibrate this laser and then perform many OCT measurements with this as a source. So we will first focus our attention into having a uniform wavelength step, investigating the filter tuning filter by filter. we can start saying that the previous approach of sweeping only the voltage is correct for the coarse and the medium filter setting, so we can obtain uniform wavelength spaced and uniform frequency spaced lasing wavelength when we send a uniform space in voltage control settings. But that's not enough, because the space between the wavelength is usually too big for achieving the 10 GHz spectral sampling of OCT. So we need to investigate the fine filter first. And we take a point for the voltage of the coarse and the medium filter, and we investigate the behavior of the fine. And we see that if we keep the longitudinal cavity mode fixed by varying the voltage on the phase modulator of the fine filters, we have these jumps in wavelength, but the best signature is given by the side mode suppression ratio. So we have the filter moving that is nicely exciting a single mode laser peak, and before switching it just drops and then build up the second wavelength. We can see that this is repeatable for many configurations of the coarse and the medium settings, and also the nice side mode suppression ratio feature is repeated over different points. So we can really take a map of a priori points for the coarse and the medium filter and try to sweep only the fine filter and see how it jumps. If we want to increase the resolution, so to have even better wavelength selection, what do we need to do? We need to tune also the cavity mode. So we need to tune the effective length of our cavity. And we do so by applying the same reverse bias to the two arms inside the filter or inside the outcoupler in this case. And in this way, we can see that we are limited by the resolution of our spectrum analyzer of 10 picometers, 1 gigahertz. So in principle, we can also achieve better resolution than that, and so having a smaller step in wavelength. As a drawback, our phase modulator are too short in this design, and so we cannot cover the full free spectral range of our cavity. So here we can see that we cover only 50 picometers when the full free spectral range is 90 picometers. So it's a trade-off. We want the cavity shorter, so the modes more spaced in frequency, but then we cannot achieve the full 2π tuning over our phase modulators. Is this approach feasible to calibrate this laser for optical coherence tomography? And the answer is that depends on how much time it takes. Because as we've seen before, we have also the problem of poor reproducibility that was less than 50% within a nice target of, let's say, 10 gigahertz. So we try to investigate what the laser does when it runs for a very long time. And we try to set the same settings over the filter and the variable outcoupler and try to record the lasing peak every 2 minutes. And we see that the laser jumps. Usually the jumps are smaller within the resolution of the OSA, so 1 gigahertz, but sometimes you can have very big jumps of almost a free spectral range of the fine filter that is 0.9 nanometers. We think that is the temperature variation on the chip. So we are controlling the substrate temperature, but we don't know if the temperature is uniform. But and we think that when we apply current, we will have some temperature variation in our laser. So we try to just move the substrate temperature from 8 to 20 degrees to just check how the lasing wavelength is affected by that. And we found that it's a linear slope of 120 picometer per degree. Since we can control the temperature, but would be very difficult to control the temperature in a fast way, we need to find a fast control strategy to ensure the reproducibility on our control settings and on our lasing wavelength. So what do? We just try to apply an active feedback system to our control settings in order to stabilize the lasing mode after we read out every optical spectrum optical lasing spectrum. And since a slow feedback is not enough, because we have a requirement on the calibration time in order to ensure reproducibility, we want to have fast feedback. So move the fine filter sweep and the longitudinal cavity mode. In order to be faster, we want to avoid also to measure with an OSA because it takes too much time. We place a tunable grating filter at the wavelength that we want to target, and then we maximize the power with the detector. And in this way, we check with the OSA if we end up in the correct wavelength. In this way, a search for a single mode wavelength takes from 1 in the best case to 30 seconds in the worst case, but is a decent speed, so we can obtain enough number of points within 4 hours and ensure reproducibility. So here we made a test and we tried 10 different coarse plus medium configuration, and by sweeping the fine filter and the longitudinal cavity modes, we see that we can have 90 picometer, that is 10 gigahertz star size wavelength with a small error of less than 10 gigahertz itself, that is the free spectral range of the cavity. So we can say that we are more or less always on the desired longitudinal mode of our laser. With this, I would like to conclude and state the main results that we obtained. So we found a tunable laser system with the 90 nanometer tuning range, thanks to the introduction of the variable outcoupler inside the cavity. We found quasi-continuous tuning when the wavelength resolution is only limited by our method of detection, in this case 1 gigahertz for the spectrum analyzer. And we found a strategy with a priori coarse and medium filter settings and try to vary in a fast and reliable way the fine and the cavity mode settings. As a further improvements, we want to develop an optimization algorithm to look for the fine tuning and the cavity mode settings in a better way and make our calibration even faster. So we are trying to exploit the genetic algorithm or the particle swirl optimization algorithm, and we will produce a new laser design with longer intrafilters phase modulators in order to improve the range of the cavity modes tuning. As a further studies, we want also to study the wavelength switching time in simulation in order to simulate more or less the full scan, the duration of a full OCT scan. With this, I would like to thank my colleagues of the Photonic Integration Group and the fundings for the project.
Thank you very much. We have time for one quick question. Are there any questions? No, it seems there's no question. I have a question myself. In slide 11, you have shown that you have quite a huge variation of the output power over the tuning range. So I guess this is a quite important issue for the optical coherent tomography application.
Yes, that's true. So this variation of output power, we think, is related to the gain curve that we have a threshold. And if it's smooth, we can accept that, more or less. Of course, we would like to have flat power everywhere, but we cannot have gain median that gives that flat power yet. But the most important thing is that sometimes we have gaps that we think that they are related to MMI coupling reflections. So we want to take also different configuration of the output coupling during our scan. And this is the one that maximizes the range. But if we want to address the gaps, we need to switch also the voltage of the variable outcoupler somewhere else.
Okay, thank you very much. Let's move to the next talk. Next talk is given by Lars Nielsen. It's a contribution from Aarhus University, and the talk is entitled "A Technique for Extracting the Carrier Lifetime of a Reversely Biased Optical Semiconductor Amplifier with 2 free-running lasers."
Thanks. Can you see my
yes,
my slides?
we see. Yes.
Okay, great. Yeah, so thanks for the introduction. I'm Lars here, and I'm from the Integrated Photonics Group at Aarhus University. So I will talk to you about my work that has the title "A Technique for Extracting the Carrier Lifetime of a Reversely Biased Semiconductor Optical Amplifier with 2 free-running lasers." This is the agenda for my talk. First of all, I will go into an introduction. After that, I will talk about the technique itself. And then I will show the technique in action, so to say, with an experiment and some results thereof. And then I will end with a conclusion. So let's dig into the introduction. So why do we need a value for the carrier lifetime at all when looking at an SOA? So my background for this, I've been looking a lot into mode-locked laser diodes and try to model them. And you quickly realize that it's not always possible to get the value of the carrier lifetime, both for reversely biased SOA, but also for a forwardly biased SOA when you use a specific platform. So therefore, I had the need to come up with a way to measure this, and I was interested in getting the value for this when I worked on a specific platform. Because I mean, these values are very important to mode-locked lasers. It basically determines the dynamics of the mode-locked laser. So how do you typically do these measurements of the carrier lifetime? And why do we need a new technique? So I would say that the most default way to extract the carrier lifetime from an active medium, if you have very fast recovery times or carrier lifetimes, is with the pump probe experiment. So basically you saturate your element with a pump, and after that you inject a probe at different time delays to see how the absorption or the gain recovers, and thereby extracting the carrier lifetime. But that is a quite complex technique, and it's not always accessible in all optical laboratories, and certainly not in the one that we have in Aarhus. So that is why I started the work on this. I mean, how to come up with a simple and fast technique for extracting this carrier lifetime with just using default laboratory or equipment in the optical laboratory. Yeah, so that was sort of the reasoning behind this. Now I will dig into the technique for extracting the carrier lifetime. So first of all, I needed to come up with some theoretical framework for this, and also, I mean, an idea for an approach. So if you look at the picture number 1 here, you can see the approach or the idea. So you take 2 lasers and you interfere them in the same fiber, and thereby you get an RF intensity modulation, and the frequency of that modulation is basically the difference frequency between the 2 lasers that you have. So then you can basically tune so to say, the RF modulation by sweeping one of the lasers. You inject this to an SOA. This SOA will have a transfer function that will depend on the frequency of this modulation, and output another RF modulated light at the output. And that way we will detect with an ESA, a photodiode in front of an ESA. So that is the idea, to see how the SOA transfers this RF signal. In order to see this theoretically, we start with a gain rate equation, the one that you see to the bottom left here. We do a small signal analysis on this, and then we end up with a transfer function, basically. And you can see that you have 2 different cutoff frequencies, and these cutoff frequencies, omega C1 and omega C2, they basically include the carrier lifetime as one term, and the other term is dependent on the average input power that you give to your system. So how do we utilize this this transfer function to get the carrier lifetime in the lab? First of all, as I said before, you fix the frequency of one of the lasers, and you sweep the frequency of the other laser. Thereby, you basically sweep the error frequency, and then you record the output power that you measure at the specific frequency on the ESA. You do that for multiple frequencies, and then you fit, and in the second step, you fit the transfer function that I just showed before to your data. And from the fit, you can extract values for the different cutoff frequencies. This is shown schematically here, that you have this shape of the transfer function. You have two cutoff frequencies. By fitting, you can get a value for these cutoff frequencies. Then you go to step 4. You do this for different values of the average input power, which is the P in DC. And that basically means that by having multiple points, you can do an extrapolation towards an input power of 0, and then get the 1 divided by the carrier lifetime. That is sort of the approach. Now I'll move on to the experiment and results where I use this approach.